I think this diagram here makes for a very interesting thought experiment, puzzle, or brain teaser, or whatever you want to call it. What other people call physics and math problems, I call brain teasers or logic puzzles. These kind of puzzles are way more fun than jigsaw puzzles. They're really challenging also. I figure if you put a wrong piece in a certain place on a jigsaw puzzle, eventually you'll figure it out because you get to the end and you'll be missing a piece. But to solve these sort of physics or math problems, they require a long string of equations and logic. So if you head off just barely on the wrong path toward the beginning of solving all these equations, then one wrong move leads to another, and that leads to another. So at the end, you'll end up with a very wrong answer. So it's kind of an analogy to what can happen in life. If someone gets started off just barely on the wrong path early on, then one bad decision can lead to the next, and those bad decisions can escalate. So throughout my life, I've heard of parents or teachers trying to get a kid back on the right path. So in regard to math and logic, this puzzle right here is a good example of what can happen if you make an error either in your calculations or in your logic early on. And I mentioned in one of my earlier videos that this can actually happen. I think it was the video about where you can find the diameter of the moon by using a star. I mentioned that every once in a while I get one of these really long puzzles or really long complicated math problems. And if you make an error early on, then it'll send you off on the wrong path. So this was one of the best examples of where that could happen. And while I don't like putting out wrong videos or wrong information, it's actually really enjoyable for me because I figure nobody would want to play a video game that's so easy that you can easily beat it on your first try. That would just be extremely boring. So it's the challenge that makes this fun, even though that does lead to occasional wrong answers. So hopefully I've cleaned up all my errors, I backtracked, and I took the right or the correct logic path now. But I try to show all my work, so if anybody sees any mistakes, then they can point it out and I can try again. So yeah, this was a lot of fun, but it was unfortunate I made a couple of bad videos with bad logic. But also, I think it's kind of like giving a tour in a city, or if you're going down a trail in the woods and you're giving a tour. If you're the tour guide, then the people that are with you might want to know what happens if you go down this path or down this street or that street. And so, yeah, I can tell you what happens if you go down those wrong paths, and I'll do that here. It's kind of fun. Okay, so this is a really relaxing puzzle or thought experiment, I think. I used to think about this when I was drifting off to sleep a long time ago, and I thought it was seemed super simple. You have a rack and pinion gear system here. There's the rack on the wall that goes up the wall. There's the pinion gear that turns. There's a big lever that comes out of this pinion gear right here. And let's just say for the diagram that this pinion gear is in a track system that holds it up against the rack. So what we have here is basically just a boat trailer jack. So anyways, we got this pinion pressed up against this rack. I put a track behind it here. So this circle coming out of the middle of the pinion gear, these are like some roller bearings or ball bearings that stick out and push up against a track. And this track is just metal bars that sandwich the pinion gear in there so it holds it up against the rack. You could also have the braces come out to the front and clamp onto the front of the wall right here. But anyways, I'll just pretend this is a frictionless system for the math, so no coefficient of friction or no mu. The pinion gear has a radius of 4. Let's also say that this lever that comes out of the center of the pinion gear, this lever protrudes out even farther towards us as the viewers, and it passes in front of this wall right here, that wall that has the rack on it. So the wall is actually behind this lever, so this way the lever can rotate in any direction and not bump into anything. So what's kind of fun is to imagine where could this person hang to be able to lift the gear up in the air. And as the person goes out farther or comes in closer, how close can this person get until the gear starts to fall and roll down? You can tell here if the pinion gear rolls clockwise, it'll fall. Counterclockwise, it'll climb. So I just said here for one scenario, you could say that the force of the man equals the force of the gear center or the pinion gear center right here. I've changed this around here. What is that pinion gear? PG for the center of the pinion gear. So anyways, force of the man equals the force of the gear, equals the mass of the man, equals the mass of the pinion gear. It also equals G for acceleration of gravity. It all equals 1, so it makes easy math. So as you slide this man back and forth, does the man go up and down? Does the gear go up or down? And then I wrote here, how far will he fall? So if he climbs way out on this lever right here and comes down, will he fall and be directly underneath the pinion gear? Or will he fall out to some angle? Okay, so I'm going to tell you what made me interested in this was every time you think about this a little bit harder or a little bit more, you're going to keep discovering questions that are unanswered. So first off, I think you might be able to imagine if this is a really long lever or a really heavy person, he's going to swing down. And what I imagine would happen was, this is a gear, and everybody knows when you have a lever on a gear that the center of that gear is a fulcrum for the lever. So I just imagine this person would just drop down, straight down like this at 90 degrees, and that lever would just go up. But that's actually not the case at all. Also, I started thinking about, since the gear, typically the fulcrum is in the center of the gear, if this man comes over here and hangs, say right here between the pinion gear and the rack, he's going to create a counterclockwise turn on this pinion gear and make it climb. But then you might notice that this rack seems to be the fulcrum because this pinion gear is hanging on one side of the rack, the man's hanging on the other, and it's held up by the rack right here. So I wrote F sub R, which is pushing up. So this rack, that's part of the rack and pinion system, this forms like the fulcrum of a lever. So if it's the rack that's the fulcrum, that means if the person comes over here and hangs to the right of that rack, then he's going to cause this gear to turn clockwise and fall. But if the center of the gear is the fulcrum, then if he hangs here, it'll cause the gear to turn counterclockwise and climb. The first error I made, or one of the main errors I made, was I recognized this rack as the fulcrum system, but since everybody knows that the center of the gear is also fulcrum, I figured that once this guy fell down and he was past that rack, then the center of the gear became the fulcrum. So it seemed like that this the rack right here made a fulcrum that just appeared and disappeared whenever this lever was horizontal. So when it was horizontal, the fulcrum appeared, and then when the lever dropped down, then that fulcrum disappeared, and the man was able to hang from the pinion right here, and the center of the pinion was the fulcrum. Yeah, but it turns out that's wrong. The real answer is just as weird. By the way, I only had a couple of semesters of physics, what they call the freshman introductory physics or whatever. So really all you need to know for this, to start solving this puzzle, is force times distance equals torque. So if you have a teeter-totter here and you got one kid on each side of the teeter-totter, then you just take the force of any individual kid and their distance from the fulcrum, and that tells you the torque. Typically, I think I've heard the standard before is to go a clockwise rotation is a negative torque, counterclockwise is positive. At least that's what I've seen before, but that's arbitrary. You can do whatever you want to there. So anyways, pinion gear is 4. The radius of the pinion gear is 4. So I'll start showing some of the math and the logic here. I'm going to start out with a normal gear here just to get warmed up. You got points A, B, and C. The line segment AB is a lever, BC is another lever. We're going to say that point B here, that's the center of this gear, it is the fulcrum, which means it is fixed, it cannot move, and so there is no rotation if you push on a fulcrum. And right here I said that point A has a force pushing up on it, creating a clockwise rotation, which will be negative. So that means to counter that, we need to push at point C counterclockwise. You just take the sum of your torques here about B right there, which will be the torque of A plus the torque of C. Force times distance equals your torque. Clockwise will be negative, so let's say that the force of A here is just 1/2, and it's 4 units away from the center, so it's 1/2 times 4, which equals 2, plus force of C times 8, because I'm going to say that segment BC here, I forgot to write that, equals 8, and line segment AB equals 4. There we go. So we just plug in numbers, force times distance. Force of C only needs to be 1/4 then, because the lever is twice as long. So I'll show more on the next page. Anyways, this is really simple, just showing how a lever works and how the fulcrum works in the center. And so now every page will get a little bit more complicated. I wonder if the upper level physics or engineering classes teach this specific example. I could see maybe engineering would, but then I wonder if physics gets into more modern physics with the upper level classes, and they don't do as much with the Newtonian stuff or the mechanics, but I don't know. Either way, I actually had a lot of fun figuring this out, and I'm having a lot of fun with this puzzle, so I'm glad I wasn't taught this in class, because otherwise if I was 19 or 20 years old and having to sit in class and learn this in addition to like 4 or 5 other classes, then yeah, it wouldn't have been as much fun. So I had fun just trying to figure this puzzle out on my own. Okay, so now we have more of a system here that looks like the rack and pinion. Here's the F sub r, which is the force of the rack pushing up. We have our pinion gear here, torque to rotate. So since we have a big circle right here and we have a force pushing up on the left side, that means we need to have a force pushing up on the right side. The center of mass for this whole pinion gear will be right in the middle, which I labeled as P for pinion. Also for the calculations, we can pretend that this whole pinion gear is massless or weightless, except for the very center, a little infinitesimally small point in the center of this pinion gear is where all that mass and force is located, and that point is what we'll use for the calculations. So for example, that point will be 4 units in from the circumference because the radius is 4. So we just look at this point right here and consider this the center of a two-dimensional table. So if you have a mass pushing down or a force pushing down of 1, and you'll have a table leg on each side, then that means each table leg has to push up with a force of 1/2. That means F sub r pushes up with 1/2, F sub m pushes up with 1/2. That's the force of the man. We can pretend he's just standing here and pushing up on that point. You can take the sum of your torques about r, point F sub r right here, that's the torque of the pinion, plus torque of the man has to equal 0, negatives counterclockwise. Torque is force times distance. Just take their forces times their distances. So the force of the pinion gear will be -1, creating a clockwise rotation. It's 4 units out. Force of the man we don't know, but he'll be 8 units out. Solve for F sub m, you get 1/2, and it's positive because he's pushing in a counterclockwise direction. So I already talked about a logic error where I was saying I thought that the center of this pinion gear was the where the fulcrum was, and what that means is you can't push on a fulcrum because you don't get any rotation. But my other error right here was I took the force of the man to be 1/2, but then since that logic error then led to an arithmetic error because I calculated this man's torque from the center of the pinion gear instead of all the way over to the rack. So I calculated his force pushing up here, sorry, his torque pushing up as 2, which is 1/2 of a force, times 4, because that's the distance to the center, that's the radius. So I came out with 2 instead of 4. So as the fix said in the 80s, one thing leads to another. So I went down the wrong path and then kept taking wrong turns. I assumed that the center of this pinion gear was the fulcrum, so that meant you could push anywhere with the same amount of force, but that was wrong again. And like I said, one thing leads to another. So next page. Now I have a car tire sitting on the pavement with different points, A, B, C, and D. What happens when you push at each point? Can you push with equal force on all points to rotate this tire the same? And say it's a tire that's in the sand or some mud, a little bit of sand or a little bit of mud, so it'll require some force to rotate it. Are all these points equal? And the reason I'm showing this is because if we take this picture here of the man hanging from the pinion, turn it 90 degrees counterclockwise, we get the exact same picture. We have a tire right here on the street. So I just said here, if friction is present, like I said, some shallow sand or something, and a force is applied to either A, B, C, or D, rank the forces needed for each location from least to greatest. And I said here, basically the fulcrum is not the point of rotation. So the point of rotation here is actually going to be the center of this car tire. As you're spinning it and rotating it, everything's going to rotate about the center, but that's not where the fulcrum is. And therein lies the rub. I thought that since the center of the pinion gear was the fulcrum, everything rotated about it, and all these points are symmetric about that center, then you could just push with equal force on all points to rotate this tire. But here's what led me to find out something, or find out the truth. If you push at point C right here, nothing will happen. Thus, that shows that point C is the fulcrum. And how I discovered this was I just took a roll of toilet paper, preferably use a new roll because then it won't unravel and it'll be the heaviest. And just scotch tape a pen or pencil to the side of that toilet paper roll so it looks like this. And then take some sandpaper, scotch tape some sandpaper to a tabletop, and then put this roll of toilet paper on that tabletop and let the pen or pencil hang off the edge so it looks like this, and it creates a lever. And you'll notice that since the fulcrum is right here where the rubber meets the road, or where the tire meets the pavement, or the toilet paper meets the tabletop, if you push on this lever, if you push to the right, if you push to the right on this lever, between the table and the center of the roll of toilet paper, the toilet paper will rotate clockwise and go to the right. But if you push to the right down here below the tabletop, then the toilet paper will rotate the opposite, counterclockwise, and it'll go to the left. And for the analogy of this man hanging on the pinion gear, that would mean that this pinion gear will go up if it goes to the left or if it turns counterclockwise. So I was thinking that the fulcrum at point C right here was present whenever the lever was hanging down between the rack and the pinion. But then once that lever moved, like say over to here, then that means you can apply a counterclockwise torque in between the circumference and the center of that wheel, and now it'll rotate counterclockwise. Thus, that seems to indicate that the fulcrum is actually in the center of the wheel and not where the rubber meets the road, so to speak, or where the pinion gear meets the rack gear. So basically what I thought we had here was a fulcrum at point C that just appeared and disappeared whenever the lever was on top of it. But the real answer, I think, is just as weird. Okay, so to answer the question here, point C is the fulcrum and actually remains the fulcrum. So if you push at point A here, you're at the farthest distance from the fulcrum, so it'll be easiest to rotate the tire. Then B will be second easiest, D will be third easiest, and if you push on point C, then it won't rotate. Oh yeah, so the whole point of this story was hang your pin off the table, push on the lever right where that fulcrum is, and the toilet paper roll will not rotate. It'll just slide and scoot along the sandpaper. I use that sandpaper because it works as kind of an analogy for the rack and pinion system where the gear teeth intermesh, so it kind of keeps the toilet paper roll from sliding around. So yeah, it turns out point C stays as the fulcrum the whole time. All a circular gear is levers arranged in a circle, and with the fulcrum being in the center of that gear typically. But in this situation, the gear or the circle rotates about the center, but the fulcrum is at point C. Okay, so that takes care of how hard you need to push on each point, or how much force you need to apply to each point to rotate this. But my next question is, in what direction should that force be applied? For example, if you have point B right here, we know the fulcrum is at point C. Should we imagine a lever that goes directly from C to B, and we want to push perpendicular to the lever, so that means we need to push up at a 45-degree angle to the left? Or do we imagine a lever that goes up from point C to the center, and then from the center to point B, and we want to push perpendicular to a lever, so that means we want to push directly up, which would be tangential to the circle? Or since the center of the circle is free to translate back and forth, or just move back and forth left and right, what if we push directly into B and push directly into the center of the circle? So in which direction do we apply the force? I've got another picture I'm going to show instead of this one. Here's the same picture. All I did is I took this picture right here that's on where the wheel's on the floor, and I just turn it 90 degrees clockwise. So now we have a climbing pinion gear like the picture on the left. What we have here is just a lever coming out. I drew a phantom of the pinion gear so that we can just focus on the lever. The force of the pinion gear is going to push directly down on this lever. The fulcrum will be right here. I'm going to call this, I was going to use F for fulcrum, but that also means force. Actually, I'll just write out fulcrum right here. So here's the fulcrum, here's the lever coming out of it. The force of the pinion gear is pushing directly down. then that means logically if we have point A right here, we can push directly up or push directly towards the center of this pinion gear and counteract that force. Here's what I imagine. Imagine that there could be some teeth right there between the rack and pinion. So there's teeth on the gear, but right here on the bottom part of the gear, this is smooth. Imagine we have a stick with a frictionless wheel on that stick. That means we could use this stick to push directly vertical towards the center of the pinion gear. And then this will cause the pinion gear to rotate counterclockwise and climb. But since we are dealing with a gear that would have teeth all the way around it, that also means we could apply a tangential force to point A right here, directly to the right, and that will rotate the gear and it'll climb also and waste no energy and waste no force. I wonder if point D would be different though. I'm thinking with point D we could not push directly vertical, because if we had any kind of a stick with a wheel on it, then that wheel is going to, the circumference of that wheel is going to push right here exactly at point D. That's going to create a force vector that goes off at about a 45-degree angle. So I wonder if we could do some sort of wasted force check where we have in this thought experiment, you could put a scale right here on the by the fulcrum where the rack is, and you could also put another scale over here where the track is. And if we're pushing up right here at point D, then what that's going to do, it's going to create a 45-degree force vector off in that direction. And if you had a scale over here, I think that would increase the weight on the scale or increase the force on that scale and show wasted energy, perhaps. So it looks like, to be safe, just always push tangentially to the surface of the wheel right here. Or in other words, push on the teeth of the gear. Or in other words, push in the direction that the motion will happen. And to tell the truth, I'm not really sure what would happen if you push in other directions, other than like what I said, if you had an imaginary scale on each side. I could imagine if you're pushing directly into those scales at some angle, then that would create a wasted force and wasted energy. So I'm not sure about any of that stuff. I'm just figuring all this out, and that's all part of the self-guided tour. I think there's another point worthy of consideration, at least for a few seconds. Over the long term, as you're watching this pinion gear rotate counterclockwise and climb, the gear will obviously be rotating about the center of that pinion gear. But that's more over the long term. I think if we think about an instantaneous point in time, and when I say instantaneous point in time, I'm thinking that we could imagine just taking a photograph and freezing all movement. We're going to be looking at a lever that comes out of the fulcrum right there where the pinion meets the rack. And I think a couple of definitions or ways to describe a fulcrum is, first off, it's fixed, it doesn't move. And secondly, it's the point where everything rotates around. So as you can see, even though the pinion gear rotates around its center of the pinion gear, we also have a lever coming out of the fulcrum, and everything is going to rotate around this fulcrum where the pinion meets the rack. And next page. Now what I drew here is just a lever system, so it's going to be the same thing as this rack and pinion right here, but we can imagine that this lever comes all the way down and is at 90 degrees hanging vertical. The fulcrum will stay at point A, so point B is the center of the gear, but I just drew a phantom of the gear because in this case we're going to pretend that there's no circular gear here and this is just a lever. So let's say point A is the fulcrum. It is located at position 0 right here. So what happens then, as we push on point C counterclockwise, it's going to lift point B up in the air, and point B will be above point A. And notice also this pinion gear here, or the phantom of the gear, actually gets pushed to the left. And that's because A is a fulcrum that cannot move, and so everything rotates about A. And I said here A is the fulcrum. Nothing happens if you push on a fulcrum. You don't get any rotation. A is also fixed because fulcrums are fixed. That's why nothing happens if you push on them. Rotation will be around A. The distance for the torque will be the line segment of AC. So since point B right here is not the fulcrum, that means you could actually connect just a line from A to C, and that'll tell you how much torque you have. And the longer that line segment is, the longer that lever is, then the more torque you'll have given the same amount of force. And I just said here, I'm just doing free flow thinking here, just writing down all my free flow thoughts. The max height that B can be lifted will be the line segment of AB. So this line segment AB, as you twist this up, line segment AB will be the maximum height. And right here, I just said that the gear is swung to the left of A, and I put gear in quotation marks because it's actually not a gear, it's just the phantom of where a gear would be. But notice that the edge, the left edge of this pinion gear, if there were a gear there, it would swing to the left of A right there. And this is different than what would happen if this pinion gear was on a rack, and I'll show that on the next page. All right, so some reasons I got my last couple of videos on this wrong. First off, I don't learn this stuff in class. I prefer to take self-guided tours. And what happens on self-guided tours is sometimes you'll take the wrong path or the wrong street. Also, I was believing that there was a fulcrum that would appear and disappear whenever the lever was over it. It turns out the real answer is just as weird. It's actually a migrating fulcrum. The fulcrum actually continually moves as this gear rotates. Okay, so I'm drawing, I drew two gears here. The one on the left is just a phantom of a gear, and it's a lever. And then the one on the right, it's actually the same lever, but it just shows what happens when you twist this, and the lever is attached to a pinion gear. So it's a lever on a pinion gear as opposed to just a lever. So line segments A, B, and BC form a right angle. So as you twist up C, you can see here that the fulcrum at point A is now below B. And that's what happens here. Point A is now below B, but the fulcrum has actually migrated, and the fulcrum is now point D, where the rack and the pinion gear teeth intermesh. So I said here that A is no longer the fulcrum because the fulcrum has shifted up to D. Then D becomes the fulcrum. You could consider D being fixed because if you push on a fulcrum that's fixed, it doesn't move. So I guess that's kind of the definition of a fulcrum. It means it's fixed and it can't move. However, while the fulcrum is fixed to the rack right here, it actually migrates around the pinion gear as the pinion gear spins or rotates. So the point of rotation is around B, yet the fulcrum is actually D. And that's different because usually with a gear or with any lever, the point of rotation is also the fulcrum. So this is weird because you have a fulcrum and a point of rotation that's actually separate from the fulcrum. And distance here for the torque of C, just draw a dashed line from C to D, and that is your lever, or that is the length that you measure for your torque. And then you can actually imagine this whole lever here is just a triangle. You can see the triangle is made by points D, B, and C. So point B provides a force in a clockwise direction, clockwise rotation, which will be negative. And then with C, you can push counterclockwise to counteract B. And then just continuing with some of the free flow thinking here. Let's see, the maximum height of B equals the maximum height of the rack. So while over here I said the maximum height of B is just the length between A and B because A was fixed. Here, since we're dealing with a pinion gear, the maximum height, it can just go all the way to the top of the rack. And then here I said the pinion stays on the rack, while over here if you had a pinion gear, it would be rotated to the left. And next page. I think it's funny to think about how this channel started just because I was curious about how to derive Pythagorean theorem and pi. And those problems were just like 5 minutes and just involved one page. But now these math problems have evolved into like 10 or 15 page problems that take like 30 or 40 minutes to solve. So yeah, kind of funny how that worked out. So at any rate, now that we've established that the point where the pinion meets the rack, that is the fulcrum, I'm going to change this page here just a second. Here we go. Okay, so here's some things I would not have guessed. Since this is a fulcrum right here, we're dealing with a lever that goes out to the center of the pinion that goes, so you have a point F sub R, then you have point F sub P, which is the force of the pinion gear pushing down, creating a clockwise rotation. Now let's say we have an infinite mass hanging right here. So let's say we have a really long lever that this guy is hanging from, and he's a super heavy guy. If he has an infinite mass, he is only going to drop down to where he is even with the rack. So in my imagination, when I was thinking about this, I imagine this lever turning all the way down to 90 degrees and sitting right below that pinion. But actually, just with gravity, that means this man is going to hang down right there even with the rack. And for him to get that close, he would have to have an infinite mass, because this rack right here is where the fulcrum is. So force times distance equals torque. So if he is just a few micrometers away or micrometers away from that rack right there, he's going to have an immense amount of force to push down right there and be level with the rack. So I just said here, the surprise is the man can never fall across the fulcrum or the rack with gravity alone. Now, yeah, if this is a toy model, or say just a model you can stand here and spin it with your finger, then yeah, you could just twist this counterclockwise and roll the pinion right up. But the man's force is determined from gravity, so that means he can actually never reach the rack. And that's because force times distance is what equals your torque. So if he had an infinitesimally small distance, that would mean he would need to have an almost infinite mass or force pushing down. And I just showed some calculations here as a reminder. Torque of the pinions, force times distance, that's -1 times 4. So it's -4 because it's rotating clockwise. And the man here, he's pulling straight down right here and rotating it clockwise. So it's, sorry, that's counterclockwise, so it's positive. And next page. So here's an analogy of, this is a little bit different here because notice the lever is horizontal. Right here you can have a lever that is not horizontal and actually goes up. Here's how you can show that this lever system is actually accurate. And this is similar to this rack and pinion system, but this page right here is a little different because it's just a lever and there's no gear. So if mass 1 equals mass 2, here's the fulcrum right here. You can actually redraw this to where the length, or that bar between M1 and M2, is gone, and you can just have both masses connect directly to your fulcrum. Mg cos theta equals your torque. So here's how you can verify that you draw a picture accurately and how you can show that it'll be stable. Meaning, how did I know to put my mass at this particular point here? M2, I guess I need to label it M1, M2. What if I put the mass of M2 way out here, or I put the mass of M1 way over here? How do I know that this is a realistic setup? Meaning that if you actually make this sort of lever and put it on a fulcrum, that the system will actually adopt these angles. And that's because of the formula mg cos theta. So first off, they're going to have equal masses and equal gravity because that's just what I decided. And I forgot to show the formula right here. You just have to set these equal to each other when you sum up the masses, because M1 will be negative because it's clockwise, M2 is positive. So you'll have M1g cos theta on one side of the equal sign, M2g cos theta on the other side of the equal sign. Masses are equal, so they cancel. The g's are equal, so they cancel. Therefore, cos theta, you're going to have cos theta 1 equals cos theta 2. The cosine is this length right here, which is the horizontal distance between the mass and the fulcrum on each side. Thus, cos theta has to equal cos theta, or cos theta 1 has to equal cos theta 2. These lines have to be symmetric. And if, let's say, mass 1 here was half the weight, then that means its cos theta would have to be twice the length to get the same amount of torque. So I think that's how you can show that you drew this diagram accurately. And again, I make all this stuff up, and I'm kind of used to being wrong because I like doing challenging puzzles and hard stuff where I can make mistakes. So at least this is just all from my logic and intuition and actually just math right here, algebra. So in other words, that's how I know that mass 2 can't go any farther than this dashed line right here. And what this also means too, that the angle of these levers for mass 1 and mass 2, the angles don't matter. So you could say the angle of the dangle doesn't matter. All that matters for the calculations is the horizontal length between the fulcrum and the masses. Now I'm going to show how it's stable. Okay, I'm going to move these pages around right here. Now remember, with all this stuff, as I always say, these are all unguided self-tours that I do. So I'm used to being wrong, but I try not to be. So I wrote here that these masses must hang at these specific angles because they form two different sized circles. So if you change the angle or change theta by even just 1/1000th of a degree, that's going to change the cos theta. And what that means is a large circle will have a large change in cos theta or sine theta. A small circle will have a small change in cos theta or sine theta. Anyways, just draw out a circle. Here we have a small circle. Here we have a big circle. We have the exact same angle right here that we can call theta. And notice that when we change this angle just any amount, and this, so we draw a line that comes out for the radius, you're going to get a smaller change on sine or cosine for the small circle compared to the large circle. So for example, here's the change in line, the change in sine for the big circle. This will be this segment right here that I'm showing. And then the change in sine for the small circle will be much smaller, so it's the same angle. And you can do the same thing for cosine. Now let's change this from a narrow angle to a wider angle. Let's look at how much the cosines have changed. The cosine will change the length of B right here. For the big circle, it'll change the length of A for the small circle. Notice that B is larger than A, and that is why this particular lever here is stable. Because if you were to push on M2 that direction and push it up, you will increase its cosine, and thus if it has a larger cosine, because this cosine right here will get longer, it'll have a larger cosine, it'll have more torque, which means it's going to force it back down. But by pushing up mass 2, you're also pushing down mass 1, and mass 1 will also increase its cosine and increase its torque, so it'll want to rotate clockwise. But M1 is rotating about a smaller circle compared to M2. And that's because the connecting rod, or the bar that connects M1 to the fulcrum, that rod is smaller than the rod that connects the fulcrum to M2. So smaller connection means smaller circle. You can actually do this experiment in about 1 or 2 minutes. Just take some Scotch tape and tape a short pencil with a long pencil, and actually tape a bunch of long pencils or long pins together to make a long rod right there, and Scotch tape them so they're at an angle that looks something like this. You can just hold this, use your thumb as a fulcrum and hold this up, and you'll notice that it will stay at a certain angle. And you can wobble this lever around all you want, but it'll always return to the same position. I actually wasn't going to show this, but I already made this toy, so I thought I might as well. You can see it took about 60 seconds to tape these things together. Notice you can push this down or up, whatever you want, and it'll always return to the point of equilibrium. And back to the regular page. And here I just said that if you have the masses, actually I said here that the masses are on auto adjust to keep the exact same angle. So you don't have to do anything, they adjust themselves and will always fall to those specific angles. If you have two masses hung, on a fulcrum here, and it's just a 180-degree bar between the two masses, then you'll have symmetric angles. So as one angle increases or decreases, the other one does the exact same. So this system right here has no preference for which mass is higher and which mass is lower, and it can spin around like a fan. So I just said here symmetric masses have no preference, and that's because these angles theta 1 and theta 2 will be equal. As one goes up, the other one goes down. Okay, next page. So now I'll finish up here showing what will happen with this man in this position right here. I forgot to mention, I hung this man out here the same distance as the radius of the pinion gear. So the fulcrum is in the middle, so the man hangs 4 units out, and then the pinion gear, the center of mass is 4 units out on the other side. But what happens, since we're dealing with a pinion gear and not a lever, that means the horizontal component here from the fulcrum to mass 2, or the fulcrum to the pinion gear, that is going to stay horizontal. It's not going to go up in the air. And then man 2 can dangle right here. You can imagine this lever falling down right here, and this is what I'm showing right here. And what I said here is with pinion gear, M2 will always be horizontal to the fulcrum. And what you can do here is you can redraw this lever system and connect M1 directly to the fulcrum. So both M1 and M2 will both be directly connected to the fulcrum. And it'll look like this picture on the bottom right here. Now here's what's going to happen. Because this pinion gear will always, its center of mass will always be horizontal to the fulcrum. So what this means is, since that center of mass is always horizontal, that means it will always have the same cosine. And what's just as important, if not more important, that cosine right there will always be at 0 degrees, which will be the line between the fulcrum and the center of mass of the pinion gear. So cosine of 0 degrees equals 1 or 100%. This means no matter how this pinion gear moves up or down, it'll always have 100% torque because the torque is mg cos theta. So the pinion gear will always have 100% torque. But this man hanging on this lever can only have 100% torque if he is hanging in an infinitesimally small area right here at exactly horizontal. So if this man weighs just a little bit more, or if he's out just a little bit farther on that lever, either way, if he gets a little bit more torque and starts to come down, his cosine of theta will shrink. Move that over there, which means his torque will shrink, and then he'll reach an equilibrium point. So like the picture I showed earlier, where if he had infinite mass or infinite force, he would just hang down right here next to the fulcrum, or even with the fulcrum. So if he has more mass or hangs out farther, or either way, if his torque increases, he's going to drop down to a certain part until he reaches an equilibrium, and then he'll just hang there. The angle will look like this. Here's the horizontal component of the pinion gear. That's the lever, or the effective lever of the pinion gear. His lever will be down, which means he'll have a smaller cosine right there, which means he'll have less torque. So I just drew a little mark right there. That would be the full cosine. You can see his cosine has shrunk a little bit. So he would be like the mass at the end of a bent lever, like I showed earlier. If something or someone were to come along and give him a little bit of a push up, that would increase his cosine, which would give him more torque, and then that means the increased torque means he would fall back down. So he would reach a point of equilibrium. On those bent levers I showed earlier, if you were to push one of those masses up a little bit, that would increase its cosine and torque, which would want to bring it back down. But if you push up this mass here on the left, then that means the mass on the right would come down and decrease its cosine. So it would lose torque and want to be pulled back up. But here, since we're dealing with the pinion gear, this lever right here always stays horizontal, so its cosine and its torque will not change. It looks like here he could change his center of mass by swinging his hips back and forth or left and right. And every time he went to our left, that would increase his torque and pull him down. And every time he swung to the right, that would decrease his torque and pull him up. So he could just swing back and forth and go up and down. Looks kind of fun. But it would get dangerous once he went above horizontal, because this cosine will shrink the same amount regardless of whether that lever goes down or up. So once that lever goes up a little bit, his cosine will have shrunk. That means he'll have less torque, and that means that's going to cause this pinion gear to drop. Once that pinion gear drops, that's going to bring this lever up, and it'll decrease his cosine even more, which will decrease his torque even more, which means that pinion gear will fall faster. So the faster that pinion gear falls, then the faster that brings this lever up, then that means the faster his cosine will shrink, and that will mean the faster his torque will shrink, and then that will mean the faster that the pinion gear will fall, and it'll be a positive feedback loop, and that would resemble a broomstick or some sort of stick here balancing on its end. Once that broomstick's center of mass goes just a little bit off center, then it will continue to accelerate faster and faster towards the ground. But if you were to draw an angle that went from the ground up to the broomstick top and take the cosine of that angle, then the more that cosine grows, then the faster that broomstick will fall. So its acceleration will increase as cosine increases. And it will reach maximum acceleration when its cosine equals 1 or 100%, or the broomstick is horizontal, whatever you want to call it. But our man hanging on this lever here, as his cosine decreases, that means his acceleration will increase. So kind of the opposite of the broomstick. And ignore my scribbles here. So I predict that if he had the same mass as the pinion gear and this was a frictionless system and he went just a little bit above horizontal like a broomstick balancing, then that could cause the pinion gear to drop really quick and fling him across the room. So I would not have predicted that at all. I would have never imagined that everything would work out the way that it does. So this was a very fun and complicated logic puzzle. And as a side quest, I got to figure out why, if you have a bent lever, like this one right here, I got to figure out why that configuration is stable, and that relates to a small circle versus a big circle and their cosines. And I also got to figure out how to draw levers accurately, giving them the same length of cosine if the masses are equal. And this also explains the desktop toys or desktop decorations that I saw a lot of as a kid. There'd be a man or some person on a small point right here, and that man would be holding a curved bar, and at the ends of that curved bar would be a weight. And now, since we understand the whole circle cosine thing, we can imagine if you push on this weight right here, push it up, then its cosine will increase, and that will immediately increase its torque and bring it right back down. At the same time, this one will go down, and its cosine will shrink, which means it's going to get pulled right back up. So it's funny how one thing leads to another. This whole project on trying to figure out a man attached to a rack and pinion system here can lead to something like this that explains toys that I still occasionally see. So yeah, this whole project is actually worth it just to figure out the balancing man. That was kind of cool. Also, that balancing man thing is just a bit of an illusion. If you were to take a paper plate or something and cut the center out of it so it's just a ring, and you dangle that ring from your finger, nobody would think anything of it. And then if you cut that ring in half, so now you have an arch dangling from your finger, nobody would think anything of it. But with this dangling man here, the bar is so thin and those masses or those weights at the bottom are so large, it creates a bit of an illusion. Also, a lampshade. Lampshades can basically be cone shapes. So if you stick a lampshade over a lamp, nobody thinks anything of it and nobody expects it to slide off. But what we have here is basically just a two-dimensional cutout of a lampshade. So yeah, I got some stuff wrong, but definitely well worth it because I learned a ton, and that's why I do these videos. Here's some quick afterthoughts to make sure I'm on the right track. What if somebody were to come along and pull him down to 90 degrees right there and then just let go? But even better, what if somebody were to pull this lever down, add a trillion kilograms or a trillion pounds or whatever, and then just leave it there? Or just let go and walk away? My first guess on this, based on just intuition, which I imagine most people would guess this, if you had an extremely heavy mass of like a trillion kilograms and put it at an extremely long lever that went down like tens of meters, and it was down here to 90 degrees, my intuition would say that nothing can lift that mass back up over to the other side of the fulcrum. But I think that this problem here is very counterintuitive. So the first thing I learned from this is don't trust your intuition. So I drew another diagram to represent this. And I learned in college many years ago that if you want to get a handle on something or kind of an intuitive feel for something, it usually helps to think in extremes. So the next diagram I have is an extreme example to help us kind of understand this. And I think it paints a pretty good picture and shows us what's going to happen. Here we go. It is the same pinion gear, but I created an extreme example. So I have these huge teeth coming out, so it looks like a paddle wheel. And way down here at the bottom, we have a super long lever. I have 10 to the 10th kilograms. I did make that 10 to the 10th to the 10th, but yeah, I didn't know how many times I was going to be writing that, so I figured 10 to the 10th kilograms would be enough. If I started getting really redundant, saying 10 to the 10th to the 10th to the 10th, it sounded a little like the movie The Big Hit with Mark Wahlberg and Lou Diamond, where one person had a tracer, so the other one got a trace buster, so then the other got a trace buster, and then someone ended up getting a trace buster. So I wanted to keep it simple here and just say 10 to the 10th kilograms. But you can see what's going to happen here. If I can get all this in the same picture, torque equals force times distance. This is going to provide a clockwise torque, so it'll be negative. So it's negative 10 to the 10th times distance, which is 18, which barely matters. But maybe you can see here, we have basically just a ledge right here. This whole thing is just sitting on the ledge. All we have is one force creating a clockwise torque that's negative. So there's nothing on this fulcrum or this teeter-totter to pull it the other way. So what would happen is this whole thing will just tilt this way until it'll rotate clockwise until that mass is on the other side of this F sub R, which is the force of the rack, or on the other side of these teeth right here. And then once this mass gets over to the other side of these this rack or the fulcrum, then its force will start creating a counterclockwise rotation. But a mass this heavy here would basically just hang right at the edge of the rack right there. In this theoretical thought experiment, where any numbers are possible and we don't have to concern ourselves with reality, since this pinion gear has a force of only 1 or a mass of only 1, compare that to a force of 10 to the 10th kilograms, which would be about actually 10 times 10 to the 10th newtons. So basically this thing right here would just hang over at a few micrometers or nanometers from the fulcrum. Quick tangent on that micrometers or micrometer. When I was in college, 20, 30 years ago, it was clarified to us by our PhD professors that the pronunciation was a micrometer was the length, but a micrometer was the little glass checkerboard thing with the reticles on it that we use to measure length of like cells or bacteria or something. But that was back a long time ago, so I don't know if those terms are still standardized or if people use them interchangeably or what, but that was a quick tangent. I found yet another error, so I'm taking this video down and doing yet another repost. But it's important to remind ourselves to not get frustrated with these little errors, have fun with them and enjoy them, because that just means it's challenging. And challenging means fun, because if we made no errors, then that would just be too easy and too boring. So if this was like a test in a physics class, it would be very difficult to get 100% on this test because there's so many steps and so many parts and so many applications. At any rate, I said the distance here was 18, and I was measuring from the weight to the center of the pinion gear, and that was wrong. The distance should actually be measured from the weight in a straight line, or I guess I should say from the end of the lever or the mass, whatever, in a straight line to where the fulcrum is, which is where those teeth intermesh right there. That's still approximately 18, but I was just measuring in centimeters. Either way, it doesn't matter a whole lot because we're dealing with a huge amount of mass and force here. Also, because this mass right here is so large, or it takes up a large area on the paper, when it comes over here to the fulcrum, you have to think about which part of this mass will hang over the fulcrum. And I think you could pick an infinitesimally small, like pinpoint dot on this mass, and that would be the center of mass. So that little dot will come over here and hang just on the other side of the fulcrum, which means a lot of this mass here will be hanging over to the right of the fulcrum. I also just thought of another nuance that would be good for this video, so I'm going to add that here. Instead of having a lever right here, this could be a large outer gear with a smaller inner gear. I've seen before that those are called compound gears, but I'm not in the field, so don't know for sure. But if you have a large outer gear with a smaller inner gear, instead of having a lever come out here, this guy right here could be holding onto a cable that wraps around the large outer gear. And it would be the same math and the same calculations. The only difference is, since he's falling straight down on a cable, then that means he could just fall forever, or until he hit the ground, or until the pinion gear hit the top of the rack. I figure you could also think of different scenarios where maybe he could be on the other side of the pinion gear. But if he's on this side of the pinion gear with a cable that goes up and he falls, it'll turn the gear clockwise and the gear will fall. So it looks like you'd have the cable come down from here where the fulcrum is, wrap around, and then come up the other side, and then go over a pulley. And then he would hang from that pulley, so as he's falling, then he's rotating the gear counterclockwise, and it would climb. But right here on the lever, this man only has 4 units of torque because he's only 4 units away. If that cable's pulling up from the opposite side of the pinion gear, then that cable will be pulling up 8 units away from the fulcrum. So if he's falling from the other side, then he'll fall faster, or the gear could be heavier. But then this would look like unequal masses hanging from a pulley. He would be like the heavier mass falling, but he would fall slower because he'd be pulling up a lighter mass. And you can see my video on unequal masses on a pulley for details on that. But back to this situation here, if he's hanging from a cable that's directly attached to a gear that makes a big circle like this, then that means he's going to fall twice as far as this pinion gear climbs, because the circle from which he'll be falling, it has twice the radius or twice the circumference. And this will also relate to potential energy. And that is because as the gear goes up 1 unit, he will have to fall 2 units to equalize the potential energy. And that's because he's attached to the gear. So if they both start out at point 0, and that gear goes up to +1 or +1, he's attached to that gear, so that means he's going to have to go up with the gear as well. But there's no energy in this gear to pull itself up and to pull him up. So the only way that pinion gear can climb is if he falls twice the distance. So the pinion gear will climb 1 unit, and then he'll fall 2 units. So the pinion gear will be at +1, he'll be at -1, and then the potential energy of the system will be 0. And I'll show a picture. Maybe I should have showed this at the beginning here of this whole part. So anyways, they both start out right here at 0. He's attached to the pinion gear. So as that pinion gear climbs 1 unit, he has to fall 2 units. And then when you sum up their potential energies, which I said here, potential energy is mgh, but m and g both equal 1. So therefore potential energy just equals the height. So if m1, the ratio of m1 to m2 is 1 to 1 because they're the same, then notice one mass climbs 1 unit, the other mass has to fall 1 unit below 0, which is 2 units below the upper mass. And if the mass ratio is 1 to 2, if the heavier mass climbs up 1 unit, the other mass has to drop 2 units below 0. So the math will work out the same whether you're talking about torque, meaning he has to be out twice as far from the center of the pinion gear or 3 times as far. But if he's out 3 times as far, that means he'll fall 3 times the distance compared to how much the pinion gear climbs. So if he's out 3 times as far, then the pinion gear will climb 1 unit, he'll drop 2 units, and the potential energy of the system will work out, because when you add these up, the pinion gear has a mass of 2, say it's twice as heavy, so 2 times 1 is 2, that means he has to drop 2 units below 0, so his distance is 2, so his mass can be 1, and then the potential energy of the system equals out to be 0. But technically it cannot be exactly 0 because there has to be some negative potential energy of the system to power the whole system, to make the pinion gear go up. So some more fun thought experiments and applications there. Also, I think I was wrong about this the first time, but I'm not really sure. How far will this pinion gear fling this man once this man goes up to above horizontal there? At first I was thinking that it doesn't matter how heavy the man is or how light the pinion gear is. Once this pinion gear starts to fall, that means it has greater torque, so it's going to fling that man across the room. But I think this might be like a 2 masses hanging over a pulley. If one mass is just a little bit heavier than the other mass, then the force of the heavier mass on that pulley, that same force now has to move 2 masses. It has to move 1 mass down and move the other mass up, so it's going to accelerate very slowly. But I'm thinking, say this man is twice as heavy or 3 times as heavy, so he's going to come in a lot closer on this lever here, and he'll be closer to the fulcrum. So we have a heavy man and we have a light pinion gear. This pinion gear has a certain amount of mass times acceleration or force to fall, but now it has to move 2 masses. It has to move itself and it has to move the man. So if I were to make a prediction, I think if you had a heavy man and a light pinion gear, I think it would just lightly bring him over or slowly bring him over, but I don't know for sure. But if you think about this in terms of the unequal masses hanging over a pulley, then that would make sense. So I think that's it for now. Hopefully there won't be any reposts. Every time I post this, I think I'm done and I'm out of ideas, but then I keep discovering little nuances and I keep discovering errors. And if those errors or nuances are significant enough, then I'll put them in the video here and make it even longer. With this particular video, or with actually most of my videos, I'm not looking for views. I don't really care about the views. This is all more for posterity, so that somebody can look back decades from now or 100 years from now or something and see this stuff and potentially learn a lot of really cool, fun information.